the time that it takes computers to process data and information could actually span from a few nanoseconds up to years. Let's focus on the time that it takes computer to process information from 1 nanosecond up to 1 second. So on one hand, we have the 1 nanosecond, which is 1 billionth of a second. If we take 1 second and divide it to a billion, because this is the time, this is the clock, the ticking time, tick, 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 that the CPU does. So each such tick is that the clock time does, each such tick is 1 nanosecond. So the time to access the CPU or to access a register over the CPU is 1 nanosecond. However, if we want to pass 1 gigabyte over the network or read 1 gigabyte over SSD, this would take a whole second. Okay, so we have the resolution of 1 nanosecond, and then we can jump to 10 nanoseconds, 100 nanoseconds, 1 microsecond, which is 1 millionth of a second, and 10 microseconds, 100 microseconds, and so on. So on 1 nanosecond, we have the CPU resolution. On 10 nanoseconds, we have the caches, one L1 and two L2 caches. 100 nanoseconds, we are still at the resolution of the CPU. It's like 10 times the CPU, 100 times of the CPU. So over 10 times the CPU, 100 times the CPU, which is 10 nanoseconds, and 100 nanoseconds, we have the L1, L2, and L3 cache. If we do an actual system call, then we jump to 1000 the time of the CPU. So a system call to do a hash or whatever to the Linux kernel will take 1 microsecond, which is 1000 times the time of the ticking of the CPU. A context switch will take 1 to 10 microseconds. We are now 10,000 the time, the clock ticking time of the CPU, which is 1 nanosecond. An LB route request will take about 15 microseconds. We are almost 10,000 times the time it takes to the CPU to process things. And on the 10,000 times the time it takes to the CPU to process things, we have a load balancer route request. We have SSD read of 10 kilobytes. We had 1 megabyte of memory copy from one cell to another, and we have an HTTP request. All of these take about 10,000 times of 1 nanosecond, which is about 10 microseconds. On 100 microseconds, which is 100 times the 1 nanosecond, we have SSD write or 10 times SSD read. SSD write takes a multiple of 10 of SSD read. On 10, and then on 100 milliseconds, we have the network time limited by physical speed of light from US to Europe. This is 100 milliseconds or 100 million of the CPU time. And then on 1 second, as we said, we have a transfer of 1 gigabyte over the network or read of 1 gigabyte from an SSD. So we see that on the lower level of the nanoseconds, we have the CPU, the registers, the clock time. It's really the hardware, L1, L2 cache, L3 cache. Then we move one layer above of 1000, the time of the CPU, and we have their system calls. It's still low level. It's the lowest level system call that we can do to the kernel. And then on the 10,000 times, we have all the usual stuff, such as reading and writing from SSD, passing packets over the network, a local network, reading from a 1 megabyte from memory. This is like the whole workforce of working with computers. And then on the slowest items of, we have transferring data from US to Europe or from US East to US West, and also reading one gigabyte from an SSD disk. Okay, so we saw a couple of layers, the layer of the CPU with nanoseconds, the layer of the still low level system calls, load balancer route, making a basic request on the microseconds, and then on the milliseconds, passing a large amount of data from one data center to another, from Europe to US, and so forth. A call to DynamoDB or to Redis or to Memcache will take sub milliseconds. So this would be just a call to get me something from cache over the network. So it would take 1 million of the CPU time.